What if you just press F11? Can maybe make it.
Yeah, which one?
F11.
F11. Okay.
Almost.
Yeah.
Maybe it's enough.
Thank you very much.
Then I'll give the word to our next presenter, who will talk about indirect reciprocity with stochastic and dual reputation updates.
Thank you very much. So I'm Yohsuke Murase from Riken Center for Computational Science, Japan. Today I'm going to talk about our study on evolutionary game theory. So we are going to talk about how self-interested agents can maintain cooperation in a society via reputation. This is a joint work with Dr. Christian Hilbert from Max Planck Institute for Evolutionary Biology. So, no. Do you know how to change the page? Scroll down. Oh, okay. So first, I'd like to talk about what indirect reciprocity is. So indirect reciprocity is a mechanism to promote cooperation in a society. Then what is cooperation? Here we define a cooperation as an act that benefits others by paying some cost to itself. So now this agent is cooperating to this agent. So this agent gets a benefit from this agent. And so cooperation is ubiquitous in our society, but why and how cooperation is maintained is not trivial, because if we naively model this cooperative behavior as a game, then it is like this. So this is nothing but a prisoner's dilemma. So the only rational choice is a defection. In order to explain cooperative behavior, several mechanisms have been proposed. So one mechanism is direct reciprocity. So in this mechanism, two players repeatedly play the game. So if you cooperate with someone today, then this guy will cooperate with you tomorrow. So you will be reciprocated directly from this guy. So in this relationship, it makes sense to cooperate because you will get a higher payoff in the long run. Another mechanism is indirect reciprocity. If you cooperate with someone, then you will get a good reputation, and your good reputation spreads to the society. Then maybe later, someone will cooperate with you because you have a good reputation. You are a good guy. So this way of reciprocation is called indirect reciprocity. And today we are considering this indirect reciprocity. To study indirect reciprocity more formally, we consider a mathematical model like this. First, we consider a large population. And every player in this population has a reputation of either good or bad. And this reputation is shared by the entire society. And population play a repeated donation game. So at each time step, randomly, we pick randomly two players, one as a donor and the other as a recipient. Let's say this bad guy is a donor and this good guy is a recipient. Then depending on the reputation they have, the donor decides cooperation or defection. The donor decides its action. And if he decided to cooperate, then he will pay some cost to benefit this recipient. Then this action is observed by the society and the reputation is updated. And we repeat this process again and again until the reputation equilibrates. And in order to promote cooperation properly, it is very important to decide how we behave, and how it is also important to decide how we assign reputation. Here, a rule that decides how to behave is called action rule. And the rule that defines how to assign reputation is called assessment rule. And we need a proper combination of action and assessment rule. And we call this combination as a social norm here. An action rule is defined by the 4 entries. So it defines whether we should cooperate or defect when good donor meets a good recipient, and when good meets donor meets a bad recipient, and bad meets good, and bad meets bad, and so on. So these 4 entries defines an action rule. On the right, there is an assessment rule. Assessment rule is defined by the 8 entries. So it defines how the society assesses the behavior, either as good or bad. When good cooperated with good, when good defected against good, good cooperated with bad, and so on. So there are 8 possible combinations. So we need to define these 8 entries to define an assessment rule. And only under appropriate social norms, cooperation is promoted. And our central question is, which social norms can promote stable cooperation? Now, let me show you some example. So let's consider image scoring social norm. This is a simplistic social norm. So, under this social norm, cooperative behavior is always considered as good. And defection is always considered as bad. So it sounds plausible, but it doesn't work actually. Because in this society, when good meets bad, he will defect against this bad guy. And then this good guy is assessed as bad in the next step. So as the time goes, bad players increases in the population and cooperation drops significantly. So this is why image scoring doesn't work. Another social norm is all good social norm. So this is another simplistic social norm. The assessment rule is defined like this. Whatever you did, you are assessed as good. So under this social norm, cooperation level is maintained high, but it is not stable because by deviating from this social norm, agents can get a higher pair. So no one wants to follow this social norm. So in that sense, this social norm is not a Nash equilibrium or evolutionarily stable. So how can we achieve evolutionarily stable cooperation? And actually this problem has been studied 20 years ago by Yohsuke and Iwasa. So this is a seminal paper in indirect reciprocity studies. And they enumerated all possible social norms and found 8 social norms that can sustain cooperation and Nash equilibrium. And these 8 norms are called the leading 8 social norms. And it is defined like this. So, and these leading 8 norms have 4 common behaviors. The first behavior is the maintenance of cooperation. When good meets good, then you should cooperate. Then, and you will keep your good reputation. The second behavior is identification of defectors. If you defected against someone who is in a good state, then you will be assigned a bad reputation. So this is the second rule, identification of defectors. And the third rule is punishment and its justification. If good meets bad, the good player should defect against this bad one. In this case, this defection is justified. Namely, this donor can maintain a good reputation. And the last rule is apology and forgiveness. If bad meets good, so bad should cooperate with this good one, and he can recover his good reputation. So with these 4 behaviors, a social norm can maintain stable cooperation. And this leading 8 has served as a basis for indirect reciprocity since then. Okay, so we're going to talk about our study. So in this study, we extended the classical leading 8 study in 2 ways. Our first extension is dual reputation updates. In a classical model, only the donor's reputation is updated. But from our everyday experience, as well as some psychological experiments, it is often common that the recipient is also subject to reputation updates. For instance, if someone is defected by someone, then we might be sympathetic to the person who is defected, and we might change the opinion against this guy. And actually, such a bias, psychological bias, is experimentally verified. And so we can, our dual reputation update framework can study such a situation. And our second extension is the stochasticity. In a classical model, reputations and actions are determined deterministically. But in a real life, some assessment might subject to some stochasticity. So it may depend on some social mood or like some mood of some person or some random other factors outside of the model. So instead of dichotomy between black and white, we introduce some gray zone between black and white. And our model is defined like this. So let's say we have two players. Alice is the donor and Bob is the recipient. And Alice decides her action based on her action rule. And now it returns the probability of cooperation. So she cooperates with Bob with probability of 70%. Now her realized action is defection, let's suppose. Then Alice's next reputation is updated as well, according to this assessment rule R1. And in addition, Bob's next reputation is updated according to another assessment rule R2. And these are also stochastic. So here a social norm is defined as a 22 of probabilities. And because the number of norms diverges to infinity, it is not easy to enumerate all possibility, actually impossible. Nevertheless, we found that this model is analytically solvable. More specifically, we derived a rigorous analytical expression for necessary and sufficient condition for cooperative ESS. A social norm, which is a set of P, R1, and R2, is cooperative ESS if and only if this complicated condition is satisfied. So if a social norm is given, by checking these inequalities one by one, one can find whether the social norm can promote cooperation or not. So I'm not going into the details of this complicated equation, but I'll share some interesting insights from this conclusion. So to get some intuition, let's consider some special cases. Here, we consider a case where social norms are deterministic and single reputation update is conducted. So this is nothing but a classical framework. So starting from this conclusion, by limiting ourselves to deterministic and single reputation case, we obtained the leading edge social norm as we expected. So the leading edge norm is derived from a different perspective. And interestingly, this is not the only solution. We found another set of social norms that can promote cooperation. We name it secondary 16 norms. And these two sets of norms are the only possibility that can promote cooperation. So how do the secondary 16 behave? The behavior of the leading 8 and secondary 16 are written like this. And overall, they behave similarly. But there is a critical difference. So it's here. Under the leading 8 norm, bad should cooperate with this good person to show apology. And then apology is accepted and this bad guy becomes a good person. Under the secondary 16 norm, this bad guy doesn't have to cooperate with this good one. Rather, he keeps defecting. Nevertheless, he will be forgiven. So it sounds counterintuitive, but when the benefit of cooperation is high enough, this social norm can still promote cooperation. So this is the conclusion of the theoretical work. And we also consider the role of stochasticity. So with stochasticity, we get a broader set of social norms that can promote cooperation. With one thing we found interesting is with stochastic reputation update, justification of punishment is not always necessary. So remember, with deterministic rule, when good defected against bad, then this good must remain good. But with stochastic rule, it may not always be good. We can consider with probability P2 that this punishment is justified. And with probability 1 minus P2, it is not justified. And we found that if P2 is strictly greater than 0, then we can maintain cooperation. So full justification is not necessary. Partial justification is enough. And such a partial justification is also found in reality. So this is an experimental work about partial justification. And so maybe I'm running out of time.
Yeah, you can take 1 minute.
1 more minute. Okay. So lastly, I'll talk about the role of dual reputation update. So by introducing dual reputation update, we again have some broader set of social norms. And we found something interesting. So let's consider this case, when good defected against this bad guy. So with single reputation update, the recipient remains bad by model definition. But with dual reputation update, some social norms forgive this recipient to be good after being punished by this good one. So both this social norm and this social norm can stabilize cooperation, can promote cooperation. But there is one advantage of introducing dual reputation update. So when we have an error, so if we have an error, someone might be like misassigned a bad reputation, or someone may like misconduct a cooperation, misconduct a defection. So in that case, because of that error, someone gets a bad reputation by mistake. And this bad reputation remains for a certain duration of time, which causes a decline in cooperation level. But with dual reputation update, it becomes more tolerant against an error. Even if error happens, then they can recover cooperation in a shorter duration of time. But there is a downside as well. So with dual reputation update, higher B over C ratio, higher benefit to cost ratio is required to promote cooperation. So there is a critical trade-off between error tolerance and evolutionary stability. To conclude, we studied indirect reciprocity with a model with stochastic and dual reputation updates. And we derived the necessary and sufficient conditions to promote cooperation. And from this theoretical result, we found several interesting consequences. And you can find some details in the paper, which was published in PLOS Computational Biology. And lastly, I'd like to thank my co-worker, Christian Hilbe, and his group members, because this work was conducted during my stay in Germany. So thank you very much.